the name of the ratio test to me kind of brings back thoughts of geometric series. Because in a geometric series, we use a common ratio from term to term to see if the geometric series itself is going to converge or diverge. So in a geometric series, what does the common ratio have to be for these series to converge? Between -1 and 1, right? So in a geometric series, if the common ratio between terms is either less than 1 or, less than 1 and greater than -1, or the absolute value is less than 1, then that series is going to converge. What we're going to run into a lot are series that are not geometric series but behave like geometric series. At least they behave like geometric series when we get out to the later terms. So what we're going to do here is we're going to compare the ratio of one term to the term before it. So this term here, a sub n plus 1 over a sub n, this is going to be a term divided by the term before it. If this right here approaches some limit as n approaches infinity, what that tells me is the series behaves like a geometric series. It doesn't necessarily mean that it is a geometric series, but it behaves like one. Okay, so what we're doing here is we're going off as n approaches infinity. So we're going to later terms in the series. Doesn't really matter what's going on early on. As the terms get really big, if we take the ratio from one term to the term before it, and those ratios are all approaching this limit L, then we can basically make the same conclusions that we made with the geometric series, with one exception. Okay, so first of all, this hypothesis here is one we're going to see a lot with these tests. It's going to be a series with positive terms, so it's going to be an absolute series again. So we'll use this to show that a series converges absolutely, and then if the series converges absolutely, if we can show that it converges absolutely, then we can also show that it converges. What conclusion do you think we can make? If this ratio here approaches some L, what has to be true about this L for the series to converge? It has to be less than 1. So if L is less than 1, then it's going to converge. If L is bigger than 1, then what do you think? It's going to diverge. Here's the difference, though. If L is equal to 1, then we don't know. The test is inconclusive. Okay, so if the ratio of one term to the term before it, or the next term to the current term, approaches some limit, then it's going to converge if that limit is less than 1, because it's like a geometric series with a common ratio less than 1. It's going to diverge if it's greater than 1. And again, the difference here is that we don't know anything if that ratio is equal to 1. It's possible that it's going to converge. It's possible it's going to diverge. Okay, so there's actually two ways this test could fail. This test could fail if this does not approach a limit. And that's going to happen a lot. You cannot always use the ratio test. There are going to be times when the ratio of one term to the term before it, they're not going to approach some particular value. And in that case, we can't use the ratio test. The other way it could fail is if the ratio approaches 1. And if the ratio approaches 1, then in that case, we're going to have to figure something else out. If you remember, I've said before, pretty much all of these tests have a way of failing. There's something that could happen that the test isn't going to do anything for us. And then we have to look for another way to do it. If there was a test that would work every time, then there's no point in having all of them, right? We could just use that one test and it's always going to work. So this has a couple of ways of not working, and we have to be aware of those while we're trying to use this.